Sergio, for this. So thank you very much for this introduction. And let me go ahead and share my screen. There we go. I'm very glad to be here today. So thank you again for the invitation. And yes, that's my goal, to show you a little bit what lattice Boltzmann is about, and to show you this open source library, Palabos, which you can just download and use for your own simulations, and a little bit the applications which we had so far in Geoenvironmental Sciences, and to see what are the kind of things you can do. And I will start right away with an example which is not in geophysics, it is in medical physics, but the type of applications you see here, you are going to see that it's a type of application which you also have in Geoenvironmental Sciences. So this is a simulation. What you see here is a vertebral bone, so a bone of a human vertebra, which is being treated by surgery. So there is a fracture in the bone, and the surgeon is injecting cement into the bone to stabilize it. This process is being simulated here. So this is, the bone has been obtained from an actual patient through a scan, and you see here the simulation of the injection of the cement into the bone, the purpose of which is to determine which is the best point and volume of injection for this treatment. And you see only half the bone, right? We removed half of the bone so that you see the cement which fills the volume. And this really illustrates the type of things you are typically going to do with lattice Boltzmann, which is applications which are in complex geometries, which is the porous media of this bone here, which is complex physics. That's the injection of the liquid cement into the bone, and also high performance computing. So this full simulation, although it works on a very high volume, is typically simulated within a range of less than 1 hour. So that's really something which is accessible real time also during the treatment of a patient. Okay, so what is lattice Boltzmann? Lattice Boltzmann is a method maybe some people don't know, so we call that a mesoscopic method, and this is opposed to macroscopic methods, which are more traditional approaches, where you just treat macroscopic variables, the ones which you are measuring in the lab. So for a compressible fluid, that's going to be the density, the pressure, the velocity, the total energy, and then you are going to solve conservation equations for that fluid. And what you see here is the continuity equation, that's the conservation of mass, and you have a conservation equation for momentum, and you have a conservation equation for energy when you are treating thermal flow. And this is the hierarchy of equations you're going to solve through some numerical analysis scheme, finite elements or finite volumes, or you name it. And in the mesoscopic approach with lattice Boltzmann, the quantity which we are going to treat is a different one. It's that this letter F here is the probability distribution function of molecular velocities. I'm going to say what that is. This is a quantity which depends on 7 scalar variables, 3 for space and 3 for molecular velocities, and 1 for time. And the equation you are going to solve is, again, of course, a conservation equation, but this time at the mesoscopic scale. So for this quantity, for this probability distribution function. So what is this distribution function about? So we are treating phase space, which is a 6D space. So 3 for physical space, and 3 for the space of the velocities of the molecules in a gas or in a liquid. And if you consider as an infinitesimally small volume around position x and velocity xi, you're going to find a number of molecules, for example, gas molecules in that infinitesimally volume, and the number of molecules you are going to find that volume is equal to the density F times the 6D infinitesimal volume. Okay, so this F is a probability distribution function for the presence of molecules at a given velocity and a given position. So this quantity F, when you discretize it, when you want to solve an equation for this quantity, there is the part which is easy to understand, which is the dependence of this quantity on physical space, because that's what we are used to doing. Okay, when we solve the differential equation numerically, we're going to take the space here. We have a flow around the sphere, which is 3D. You are going to superpose a numerical measure on the physical space, which is a discrete version, a discrete representation of space, right? So you see here a clearer vision of the mesh which was used for this simulation. And so you have points on the mesh, and these points are the discrete space positions at which the quantities which you are going to treat are being represented. And in lattice Boltzmann, we really do the same to discretize this distribution function in space. And the question is, what are we going to do with the 3 additional degrees of freedom, which are the dependence on the molecular velocities? This is where it gets a little bit tougher, and where the theory of the lattice Boltzmann method kicks in. So to understand the dependence on the velocities, maybe it is better, it is good to first understand what is the shape or the type of this distribution function. How does this distribution function look like when you look at it from the point of view of its dependence on the molecular velocities? So actually, most of the time, gases or liquids, they are close to an equilibrium state. The equilibrium state, which is the one which you reach when you know the velocity, the temperature, and the density are uniform. And in this case, you have a statistical theory which tells you that the velocity, the dependence of this distribution function, is just a Gaussian distribution. That's the Maxwell-Boltzmann distribution, which is a Gaussian curve around the average velocity, essentially. So you see here 2 examples in 1D of what this Maxwell-Boltzmann distribution can look like. So the blue curve here is the curve which you are going to have if the temperature is small, and the red curve is the case with 3 times larger temperature. So the temperature is really the variance of this curve, and the velocity is going to be the point where this curve is peaking. So when you solve the Boltzmann equation, you're going to solve for a function which varies slightly around this distribution. And when you are trying to relate what you are seeing to macroscopic variables, so you have seen that on the discussion of the curve before, to get macroscopic variables, that the ones which you are going to measure in the lab, the density or the velocity or whatever, you just integrate away the velocity dependence of the distribution function. So just the integral of the distribution function over velocity space, that's the first line, gives you the density, and the integral of the distribution function weighted by the molecular velocities, this gives you the momentum, which is the density times the velocity, microscopic velocity. And if you weight your integral with the square of the molecular velocities, you get the energy. Okay, so there's a direct link between those quantities and the macroscopic quantities, and you see that the physics which you are representing here is richer than in the macroscopic vision, because you have a function which has more degrees of freedom. But most of the time, when we post-process at least the data, we're going to look into the macroscopic variables, which we integrate like that. Now, the trick when you discretize this and handle the velocity dependence is that you want to replace the integrals above with appropriate quadrature rules. So you want to replace them by sums. Okay, so the discretization of the velocity space amounts to choosing a set of discrete velocities. That's the quadrature points in velocity space. And point number 2, the equilibrium or distribution, or just actually any probability distribution, is replaced by at every point in space, replaced by a set of distribution functions for every discrete velocity. So the velocity dependence of the distribution function is really just replaced by a discrete index over all the quadrature points. And when you evaluate the macroscopic variables, you simply replace all the integrals by appropriate sums, which are chosen, you know, with interesting quadrature rules that give exact results if the distribution function is a polynomial of a certain degree. So that's the basic idea. And as we choose these quadrature rules, there are actually many possibilities, but only few possibilities which we are interested in, because there is a link between the space and the velocity discretization. In the sense of, you see, you have 2 points here in the space discretization. And if you take quantities that are defined at one of these points, x, at a given time, then as you evolve in time, you're going to move with a speed which is equal to the discrete velocities that have been chosen. So at the next time, you will move to the position which is x plus the time discretization delta t times 1 of the discrete velocity. So those discrete velocities are always going to be chosen in lattice Boltzmann to be a multiple of integral values in such a way that as you propagate your information, you will always remain on the numerical grid. So this is really a limiting factor of your velocity discretization, and it also has an impact on the space discretization, because you are not going to be able to work with arbitrarily shaped meshes, because if you would, then you would have an incompatibility between the space and the velocity discretization. And that's the reason why in lattice Boltzmann, most of the time, there are exceptions. There are always exceptions to everything, but if you take the fundamental lattice Boltzmann method, you're always going to be limited to a uniform mesh. A uniform mesh, which is mostly a matrix, or as it is in this picture, a hierarchic structure of matrix, pieces of matrices. So let me summarize that again. In the lattice Boltzmann method, you are limited to uniform grids and lots of simulations. They are just, as on the picture in the left, 2D or 3D matrices which cover your domain, and sometimes they are what you see on the right, which are hierarchically nested as homogeneous meshes. And that's really the best case scenario, because I think it's only recent that the codes, the lattice Boltzmann codes which are out there, really use those hierarchic meshes for general cases. What are the advantages and what are the disadvantages of the lattice Boltzmann method? Let me summarize those right now and come back to them as I show you the examples. I think the advantages are on the left. The lattice Boltzmann method is massively parallel by design. When you write a lattice Boltzmann code quite easily, quite spontaneously, it is going to run on GPUs which are a parallel architecture. It is quite spontaneously going to be adaptable to clusters of CPUs or GPUs. It is a very robust method. Robust means that you have a methodology which can be very accurate for a given problem. And you know, when you are going to stretch the physical limits of your problem, things get more difficult, and maybe the accuracy goes a little bit down, but you still get a reasonable solution for the physics you are considering. And that's what I mean by robust. And this is one of the points that's often appreciated with lattice Boltzmann. It's also quite undemanding with respect to pre-processing. That's mostly, I think, because it's a method with which we work with hierarchic meshes, which are generated by so-called octree or quad tree in 2D structures, which are very fast to generate. So when in classical CFT, often you can spend a week to just generate a mesh. Very often in lattice Boltzmann, this is going to be a matter of minutes because of the type of meshes we use. It is also a method which handles complex geometries very naturally. This is why you see lattice Boltzmann popping up very frequently for problems in porous media, as you saw that in the example of the flow in a porous bone. And there are disadvantages, of course. I list some of them. So one of the disadvantages is the limitation to some types of meshes. And although with those hierarchic meshes, you can do quite a lot, you also see that in the community, people are actually struggling to port the lattice-Boltzmann methods to hierarchic structured meshes. So very often you see codes that are really just limited to a matrix shaped structure, and that has a cost at the level of efficiency. Typically, lattice-Boltzmann is low order, so it's second order in space, so similar to a finite volume approach, and so you don't have the advantages of a high order method. And the theory is sometimes a little bit tough, so people are used in CFD that you give them, a differential equation, and they just apply stepwise the methodology of numerical analysis to discretize this equation. And with lattice-Boltzmann, this is a bit different. When you have a new equation, you really have to get creative and find a way to address this new equation with the lattice-Boltzmann approach. So the theory can be a bit less straightforward. Now, after this very quick introduction to the lattice-Boltzmann method, and you definitely find a lot of literature online to learn more, let me tell you a little bit more about the Palabos software library. It is a software platform for lattice-Boltzmann simulations in many domains. It is a software platform which we wrote with the idea that we really take all the lattice-Boltzmann models which we see out there, which we see presented at conferences, and try to implement it in parallel in a given software platform, and then people can apply it to different kinds of industries. I'm showing you some industries here which are all not non-geophysics, because the geophysics part is coming right afterwards. There is fluid structure interaction on the left. That's something which we use to do cell level simulations of blood flow. So blood is essentially packed with red blood cells, which are deformable objects. And to understand the rheology or other properties of the blood, we're going to simulate that full result by solving the structural mechanics of every single red blood cells through finite elements, and couple the thing back to lattice-Boltzmann. So that's something which is part of the Palabos library. The second column mentions multi-phase simulations. There is an infrastructure for aerodynamic simulations. There is now a module for supersonic flows, just to mention a few examples. And the code is traditionally parallel on CPU clusters. And just this summer, we ported the code to GPU, which means many of the applications which people wrote for inside the framework of Palabos are now just spontaneously running on GPU. Okay. So the history of Palabos, it starts around 2005. That's quite some years ago, with the predecessors of Palabos, which are Vladimir, a library that is no longer maintained, and OpenLB. That's a library which still exists and which is actually maintained at the Karlsruhe Institute of Technology. And in 2010, we have the first version of Palabos, which is like a fork of OpenLB, which goes into the a broader direction of multi-physics, I would say. In 2011, we had a startup company, FlowKit, which was commercializing the Palabos, which at the same time also remained open source. So the code was developed jointly by the University of Geneva and this company, which then was incorporated into the Numerica company to contribute to the commercial Omnis LB software. And in parallel, you still have the open source Palabos. And since 2018, the University of Geneva and the different institute, HPI in Geneva, took over the development of the open source Palabos code. So it is, you now have the commercial Omnis LB, and you have the open source Palabos, which is continued to be developed by University of Geneva and HPI in Geneva. Okay, so how does Palabos work? The basic idea in Palabos is that you're going to have a simulation domain which is going to be covered by grid patches, which are just pieces of regular matrices. And those grid patches, they just wrap your computational domain optimally. So depending on your needs, you are going to use coarse or fine patches, as you see in this example of a flow in an artery with an aneurysm. That's again in the biomedical field. So you have on the left a coarse wrapping, on the right a fine wrapping. And this choice of those grid patches can be really static if your geometry does not move, and it can be dynamic for evolving problems. And the example I showed in the very beginning, the one of cement injection in a porous bone, that's a dynamic problem because the cement is simulated through a free surface approach, which means you don't simulate the air, okay? The air is absent from your problem, and your cement is just having a free surface that evolves, which means that as you simulate the cement evolution in the bone, you only need the areas of the bone which are occupied by cement, and the other areas are of no interest. So you can just take your cement injection point and allocate a memory only around the pieces which are filled with cement. And this is what Palabos then does. It just, reads pieces of your porous structure and allocates them around the growing free surface flow. And again, I think this is an example that illustrates how the uncomplicated handling of geometry is an advantage of lattice Boltzmann, because with other meshing techniques, you certainly could not evolve dynamically like that. And then once you have those grid patches, your problem is parallelized on CPU or on GPU. On CPU, every CPU core is just going to get one full or several full grid patches. And on GPU, that's a bit different because GPUs have much more cores than CPUs. So on GPUs, every single grid patch is going to be treated in a multi-threaded manner by all the cores of the GPU. But parallelism in both cases amounts to distributing those grid patches to all the available CPUs and GPUs. Now, when you use Palabos, you are going to write in the C++ language an end-user application that uses the Palabos programming interface. So you are going to use, first of all, a data container, which contains your distribution functions, which we talked about in the theory, and which is a parallel data container. So we have two versions of that parallel data container. We have a so-called multi-block lattice, which is parallelized on CPU, or the accelerated lattice, which is parallelized on GPU. They have the same interface, but a different backend. So you're going to choose your parallel data container depending on your hardware, and then you are going to configure your simulations. And you can there is something which is called lattice descriptors, in which you choose your velocity discretization, which is adapted to the type of physics you're going to use. You're going to select your correlation models, which are essentially the choice of the numerical method appropriate for your problem. And then you are going to write your physics. For example, if you are having a thermal flow and want to couple your fluid with a temperature field, you're going to write what we call a data processor. That's a general framework to write parallel algorithms adapted for your data container. And when you do this, this is completely agnostic of the hardware. So no matter if you are using CPU or GPU, you're going to write your algorithm and it is going to be parallelized automatically by your data container. So what you have here is, in Palabos, you have, of course, a collection of models which exist, but also a platform to develop your own models in parallel. So let me show you here just a quick extract of an end-user application, and on top you have the type of code you're going to write if you run on CPU, and in bottom the type of code you're going to write if you run on GPU. It is really the same code. It is just switching from one container to the other ones, and your simulations can also be hybrid. typically there exist algorithmic components which are going to run efficiently only on CPU, and those you are going to run them on CPU, and then when you go to the heavy duty parts, you put them on GPU. So you can have both containers in parallel and transfer data between them. So implementation wise, a lot of code is shared. So you see here the code structure. On top, you have the code base in which the actual numerical methods are implemented, in which you have the MPI backend, in which you have mesh creation and management algorithms. And this code base is common to CPU and GPU. And in the middle, you have a piece of CPU backend, which we wrote back then for CPUs, and the GPU backend, which we recently wrote for GPUs. And on the bottom, you have the end user applications, which are again common and agnostic of the type of hardware, except for one line in which you choose your backend or you choose your parallel container. And I'm saying that because we have reached a point where essentially, I mean, it makes little sense to run on CPUs, so to say, because for most problems, you have a GPU backend and it just runs much faster for a machine which has the same price. I'm running here a flow through porous media. That's the Berea sandstone. It's a sandstone geometry which is openly available and which is frequently used for benchmarks. And I'm coming back actually to that sandstone several times. And when you just run a single phase flow through that media, you can measure the performance on two types of machines. I measured it here on a CPU, which is a Xeon Gold. It's a high-end CPU with 48 cores, which is really fast and also really expensive. And when we ran it here, of course, we used all the 48 cores. And we also ran it on a GPU, which is an RTX 3090 GPU. That's, I think, it's like the best gaming GPU from NVIDIA, which you can get these days, okay? But it is really a gaming GPU. So price-wise, both machines are really comparable. And the code which runs the application is the same for both. In Palabos, you write one code to match both. And it runs actually really fast on the CPU, and it reaches a metrics which we measure in million lattice updates per second. That's a metric in which more is better. And you see that you get like 400 of those on CPU and 5,000 of those on GPU. So there is a speed up when you move from CPU to GPU, which is 12-fold. And this speed up, you get it really for free because it is for the same end user application. And then it runs also on multi-GPU. This is very, very recent. Now we just ran this a few weeks ago on a GPU cluster, which is called Selene, which has many A100 GPUs. Again, that's not the highest level, the highest cluster level NVIDIA GPUs which you get those days. And we ran this on a system which goes up to 16 nodes of 8 GPUs. So in this sense, on the biggest system which we ran, we had 128 GPUs, and in strong scaling, so in weak scaling. So when we try to fill all of these GPUs, we get a performance of 137 gigalattice updates per second. Again, for the same code without modifications, you have multi-CPU parallelism, you have multi-GPU parallelism. And there is a link here to another conference in which I'm telling more about that. So yes, that's a 40 minutes presentation of Palabos on GPU. Now let me move to applications. And the first application I would like to talk about is multi-phase flow through porous media. And you see that animation started automatically here. This is a simulation of a two-phase flow, which we modeled through a color gradient approach, which was implemented in Palabos by Sébastien Leclerc. And this movie is also from him, where he investigates, imbibition properties of the Berea sandstone, the same sandstone as I showed you before, and you have different regimes. So this is two-phase flow, so that your porous media is first saturated with one fluid, and then you inject another fluid, and one of the fluids is wetting, the other one is non-wetting. And the top animation, which I think I can maybe restart, the top animation is what you get if the invading fluid is wetting, and on the bottom if the invading fluid is non-wetting. And you have different regimes depending on the ratio of capillary forces and viscous forces. So it depends on the surface tension and on the velocity and on the viscosity. And here we are in a fingering regime where you see that the fluid is taking a preferential path to invade the porous media. And this is a typical type of application which is simple to implement in Palabos and very fast to simulate a classical lattice Boltzmann application. And another one which we ran in collaboration actually with Andrea Parmigiani and Chris Huber, who is now at Brown University, is again a two-phase flow through porous media, which is saturated first with a wetting fluid and then invaded not through pressure gradient but through buoyancy. It is invaded by a non-wetting fluid, by a gas. Okay, so it's like a porous media which is filled with water, and you have gas which is invading the media and which is crossing the media through buoyant forces. And this is a very large simulation which some years ago we simulated on CPUs actually with 2000 times 300 grid points to get the statistics of the permeability of that porous media. And it turns out that this is actually a problem which is subject to instabilities, which means that for two statistically equivalent initial conditions, you can have two completely different outcomes. And the explanation is that the different outcomes they are due to an effect called channelization, which means that at some point, as you saw on the previous slide, you have maybe a preferential, you have some fingering path which is taken by the fluid and which prepares the path for the upcoming fluid. So at some point, all the fluid takes the same path or the same channel, and that's an effect we refer to channelization. You see this for the simulation just of the above slide. You can have two different outcomes for the statistically same initial condition. The x-axis is time, the y-axis is the saturation of the porous media with the invading gas, and you see that with the green curve you can have, you know, at one point a larger saturation, and with the red curve a smaller saturation, which is the channelization instability, because different preferential paths were created in both cases. And well, I see now that there's a question, which is whether the code is able to do adaptive meshing during a multi-phase flow. And the answer is that this is currently not the case. In Palabos, we have adaptive meshing only for single-phase flow, but I will come to that in the end. This is one of our big topics of research right now, to extend actually adaptive meshing to different types of flows. Yeah, let me switch to a different application, which is the simulation of rivers and canals. And well, time goes fast, but I think I need like 5 more minutes to reach the end of the presentation. So here you have the joining between the Rhone River in Geneva and the Arve, which is, you can see that the Arve on the right is coming from the mountains, so it is really charged with sediments. And you see that it's brown, it's charged with sediments, and all of these is leaving Geneva and is flowing into France. But right before it goes to France, it will be caught by a dam. But so we are going to simulate that system with a free surface approach, which you have in Palabos. So the free surface approach, let's just start the simulation, is an approach in which you simulate the fluid, but you don't simulate the gas on top. Huh? So you see here the dam, which is right before the Rhone River enters France. And at that case, you know, all the sediments which come from the mountain, which come from the Arve, they are aggregating behind the dam. So once every 5 years, essentially, there is a river cleansing process in which the gates of the dam are opened to flush the sediments and erode the sediments and flush them, you know, somewhere else. That's a political issue afterwards. But so there's simulation ongoing to understand better the efficiency of the flushing process. So you see here on the left a simulation of the moment where the gates are opened and a lot of fluid is actually crossing the dam. And on the right you see upstream from the dam a picture of the shear stresses on the riverbed, which gives us an understanding of the erosion processes. Okay, so there is the capability of river and canal simulation and study of erosion processes. Other examples which are relevant, I would say, to geophysics are simulation of particle suspensions, which, well, here you have a three-phase flow. Now you see air bubbles, you see particles, both of them immersed in a liquid. And so there's a framework for particle immersion. On the right, you see that we get rheology laws with different kinds of densities of particles in the fluid. And the last topic, which we are working on a lot, is transport of ashes expelled by volcanoes during eruptions. So let me show you a picture of actually two eruptions, one which is in Indonesia on the left and one which is in Iceland. It's the Eyjafjallajökull on the right. So you see that you have like rains of ashes falling from the plume, and those rains of ashes, they are due to instability. And we are investigating, you know, the types of instability which can explain those fall downs, which are important to understand the place where the ashes of an eruption are going to falling down. That's a system which is multi-phase in the sense that you have different air layers with different densities, and also in the sense that you have to model the transport of ashes. So what you have is that we are coupling on top a lattice Boltzmann simulation for the fluid with an advection diffusion equation for the air layers of different density, and then actually a high order finite difference scheme, because we need to have sharp interfaces for the particle transport, and the full system is coupled to simulate that instability. And we are doing that in collaboration with the group, with an experimental group in Geneva, which is doing lab experiments with sugar and particles in a tank. And that's the left image, and on the right image we have the simulations which we reach with Palabos, and you see that we get corresponding instability patterns. Huh? So let me just see that. Yeah. Okay. So this is an example in which actually a person from geophysics was taking the Palabos code, and under our guidance was implementing actually a quite sophisticated coupling with different kinds of physics, and was able to get the capabilities in terms of simulation that was required here. Okay, so I'm reaching the end, and I would just point out the kind of research which we are doing right now to continue from where we stand. So the tephra transport for volcanic eruptions, that's a topic on which we are doing continued research in collaboration with Costanza Bonadonna in Geneva and Paul Jarvis before in Geneva, now he's in New Zealand. And we are trying to extend our models to include large-scale effects and couple actually the tephra transport with fluid dynamics at large scale that involves using compressible flows. So at the place of the eruption, you typically can have a transonic or supersonic flows, and at the transport level, different types of flows. Or maybe before moving on, let me also mention that on this topic, we are currently actually searching for a PhD. So we have an open PhD position in tephra modeling with the lattice Boltzmann method within Palabos. If anyone is interested, please contact me. Let me know. We are also working on particle suspensions to model crystal marsh. So essentially, in magmatic chambers, you have like a mixture of liquid magma and crystals, and we are trying to better understand the processes of magma extraction from a crystal marsh through numerical simulation. And for this, we are pushing forward the capability to simulate densely packed particle suspensions. We are also working on improved compressible transonic and supersonic flow models. Finally, a topic of ongoing research is to extend our capability to work with hierarchic meshes, with mesh refinement for more complex physics, but also to move that part to GPU, because it is not currently. But this is very recent. This was just done 2 weeks ago. This is our first result in 2D of a flow on a hierarchic mesh on GPU. So the simulation, the video you are looking at is essentially simulated in real time. So the GPU just computes that data in a few seconds, and the video also takes a few seconds, because we really take full advantage of the GPU speed. Sorry for that. Okay, yeah, so that's an airflow. That's a flow around 2D NACA airfoil at a Reynolds of 10,000. Good. We are reaching the conclusion. LBM is really a versatile tool for a large number of applications. It is very widespread in environmental sciences. Just to tell you a funny story, we collect actually all publications which mention the use of Palabos, and around 50% of those publications are about flows through porous media in environmental sciences or in geophysics. There is an ease of modeling the physics. There is efficient parallelization. Then you have Palabos, which is an open source code. Please just go to the website. There is a way to interact with the community to download the code. And just like the seminar which I'm speaking at here, we also have a monthly online seminar at which you can actually learn about the Palabos users and their applications. Thank you very much for your attention.
Okay.